All we're going to do today is combine Newton's laws, free body diagrams. I'm going to introduce a few new forces to you as well so that we can start to use proper terminology. I don't know if I'm going to get through the whole lesson today. We may end up continuing this on Monday. Hey, example 1. Here's our thought experiment. The tension in the rope in the bottom case is A, greater than, B, the same as, or C, less than the tension in the top case. I was going to say, once again, we have a chance to vote, but Jason, in his enthusiasm, blurted it out, and I'm okay with that. But Jason, I'm going to say, convince me.
Newton's law.
Which law?
First.
Expand it. So, ready? Newton's third is forces come in pairs. By the way, pairs, I think that's the number 2. What comes after the number 2? Newton's third. Whatever dumb way works for you. The problem is it doesn't work great because there's also a Newton's second, and you might think pairs. Isn't that Newton's second? Newton's second is the equation, F equals ma. Okay. Yeah. Forces come in pairs. No difference. Well, you could also make an argument for Newton's first law. If this isn't accelerating, if the biggest force, actually, you know what? I'll take your forces come in pairs. I think that was how I explained it. This was the bathroom scale, 2 girls pushing against each other. Same physics. Now we're pulling. Types of forces, Racy. Gravitational force. The force of gravity. Symbol, I use Fg. F with a little subscripted G. What was our equation for the force of gravity that we just started replacing on free body diagrams and not even bothering to put an Fg on there? How do we calculate the force of gravity? Mg. It's really Ma, but where G equals 9.8. We're not going to include the negative in for our force, and the reason is we know the direction. Towards the earth, and I deliberately didn't call that down. Call it towards the earth. What's another word for the force of gravity? No, now. Wait. No, now. Wait. No, now! You have no idea how long I've waited for that joke. Okay. Weight is not the same as mass. And I guarantee, in fact, you may want to even put a star next to this. I will ask you this on your test. I will ask you to find the weight of an object, and I guarantee as the first answer, I'll have to pick from the mass of the object in kilograms. That is not the weight. In fact, let's expand on that. Shelby, the ballet dancer, has a mass of 45 kilograms. What's Shelby's weight in newtons at the Earth's surface? Not 45 kilograms, that's her mass. Her weight is Fg. So it's going to be 45 times 9.8. Yeah, I can do that in my head because it's going to be 45 times 10. It's going to be 450. Take away 9. 441? Yes? Units for weight, not kilograms. It's a force. The imperial measure for weight is pounds, so when you give your weight in pounds, that's correct in terms of physics. When you give your weight in kilograms, you're being sloppy. You should say, that's my mass in kilograms. Put your pencils down, look up. Given that 1 kilogram of mass corresponds to 2.2 pounds at Earth's surface, what's Shelby's weight in pounds? Hey, this is a job for a unit conversion. How do we do a unit conversion? We always started out with what they gave me. 45 kilograms. I want kilograms to cancel. What's the abbreviation for pounds? How stupid is that as well? What's the abbreviation for pounds? Let's have two letters that never appear in the original word as the abbreviation, an L and a B. One more reason why I hate the imperial system. And I guess it's 2.2 pounds is the same as 1 kilogram. That will make kilograms cancel. But here's the important thing, Kath. It tells me I'm not going to divide by 2.2. The 2.2 is on the top, so I'm not going to divide. I can do that in my head. 45 times 2 is 90. 45 times 0.2 is 9. 99, yes? Double check me, but it should be. Yeah. 99 libs. Pounds. Let's see. What would Shelby's mass be on the surface of Jupiter? Zach shrugged in ignorance. Too slow. What would her mass be on Jupiter? You all know the answer right now instantly. 45 kilograms. Your mass is universal. It doesn't change. It's a measure of your inertia. It comes from the protons and neutrons and electrons that make up you. We're allowed to shrug for part D. What would Shelby's weight be on Jupiter's surface? Now, I realize technically Jupiter doesn't have a surface. It's a gas planet. But I wanted to go to another planet. So I dream. Where the acceleration due to gravity is 25. Fg on Jupiter, how about Fg with a little j, is going to be mg on Jupiter. Does that work, Henry, for being clear without writing much information, but I'll figure out what I was getting at? It's going to be 45 times 25. $1,125? Units. It's a force. Newtons. So she would feel heavier on Jupiter. Her mass hasn't changed. What's changed is how hard the planet is pulling on her. I wrote down here, pause here and complete section A of the homework. I'm going to put that in a bit later, but I want to talk about another force. Suppose a 12,000 Newton truck, I've given you its weight, not its mass, is sitting at rest. You know what? This is important. On the ground. Draw a free body diagram of the forces acting on it. Okay. There's the truck. What are the forces acting on that truck? Get the obvious one. In fact, I could even call it 12,000 newtons. I can even be more specific than gravity. I can actually tell you how big it is. Is this truck sinking into the ground like quicksand? Is it flying into like Superman? So that means vertically the forces must be, I'm looking for a word that begins with letter B. So there has to be a force up. It's exactly 12,000 newtons. Now, this is gravity. By the way, if I give you the weight, the force of gravity, and you need the mass, how can you figure out the mass if you know the weight? Divide by 9.8. Oh, and if you have the mass and you need the weight, times by 9.8. I will flip-flop, so just read the questions carefully. Sometimes, Alec, I'll give you the mass. Sometimes, Matt, I'll give you the weight. And that's just to see, pay attention and read carefully, because that's a good thing to build into you as well. Okay. What's exerting this force here? What's keeping the truck from sinking? Today we're going to give that force a special name. I'll tell you what it is. It's going to be in our notes in a bit. We call it the normal force. We say that when you push on a surface and the surface pushes back, forces come in pairs, that push back, we call that the normal force. Suppose we added a 2,500 Newton piano to the back of the truck. Draw a free body diagram of the new forces. There's the truck. What are the forces acting on the truck? Get the obvious one. mg, which equals 12,000 newtons. What else? Piano. Which way would the piano exert a force on the truck? down. Now, since it's in the same direction, don't write this down. I don't like trying to draw something right on top because I'll miss it. So if it's another one in the same direction, I'll just put it beside, to the left or to the right, doesn't matter. Why did I draw it shorter? Yeah, in fact, really, if I wanted to go roughly to scale, I should have drawn it way shorter than that, but shorter. And this is F piano, 2,500 newtons. Is this truck sinking into the ground like quicksand? Is this truck flying into the like Superman? So, what else? Why would this be incorrect? Why would an arrow the same length as mg be incorrect? Yeah. The ground now is pushing back harder than gravity. It's canceling out the piano and the truck. Okay. The ground will push back as hard as it needs to. Oh, and if eventually the force down is harder than the ground can push back, then you will start to sink like you're in quicksand. Mud is a great example of a type of ground that doesn't have a good pushing back force. We're not going to talk about mud very much, though. This force of the ground, or any surface, table on your binder, chair on you, pushing up to prevent the object from sinking as a special name, we call it the normal force. Symbol, I use Fn. Some textbooks will use a capital N, but now capital N stands for newtons, normal force, and north. That's too much for me. So I'm going to go with F, force, normal. Why do we call it the normal force? Is it because it's normally there? No, actually, the word normal in math means at a right angle to. Whenever you push down on the ground, it pushes back straight up at a right angle, at 90-degree angle. Or when I push against the wall, it pushes straight back at a 90-degree angle. The normal force. The normal force is a reactive force. It's the result of Newton's third law, which was, Jason, forces come in. And because it's a reactive force, the normal force will only push back as hard as it needs to. In the first example, it pushed back hard enough to keep the truck up. In the second example, since the truck was pushing down harder, piano, it had to push back harder. If somehow we had started lifting up on the truck, maybe with a crane, the normal force would have gotten smaller. It's only going to push back as hard as it needs to. It's the force that prevents us from sinking into the ground. How big is the normal force in each of the following situations? So here's a free body diagram. I guess this would be mg, which would be 5 times 9.8. Which I can do in my head. Do you know the quick way to multiply decimal? Put your calculator away, Elliot. Do you know the quick way to multiply decimals by 5? Times by 10, divide by 2. Times by 10, 98, divided by 2, 49. Gravity down is 49 newtons. Is this box sinking into the ground like quicksand? Is this box flying into like Superman? So there is an arrow pointing up, same length, and I can tell you it's the normal force, and it's exactly 49 newtons. The normal force is as big as it needs to be to keep that equilibrium. In situation B, I think I can zoom in a little bit. Hey, that'll work. In situation B, so now we have, didn't want to do that. So now we have gravity, which was 49 newtons, but something else is also pushing down. Maybe somebody off the page that I didn't draw is pushing down on this box as well. Maybe somebody's sitting on this box. I don't know. What would the normal force be? I'll draw it bigger than gravity. If I really wanted to go to scale, what I would try and do, Kirsten, is I would try and make the 30 newtons and the gravity lines that long. I would try and make normal force exactly as long as both the lines put together. I'm not going to be that fussy. That's why I said roughly to scale. Make sure what's bigger is bigger. Make sure what's smaller is smaller. How big is the normal force here? Exactly? Has to be. You're not going to get an equation to calculate normal force. You're going to use Newton's laws to figure out the normal force. Ryland is in Physics 12. They haven't heard the look yet, but that, right? We don't have an equation for normal force. We always figure it out from our free body diagram. Oh, here, someone is lifting up. So we still have gravity pushing down at 49 newtons. But someone is lifting up with 12 newtons of force. What's the normal force? How hard does the ground have to push up? Are we sinking into the ground like quicksand? No. Are we flying into like Superman? No. So forces are balanced. How big is the normal force? 37. So I'm going to draw it clearly shorter than gravity, and I'm going to say normal force is 37 newtons. Hey, question for you. What does a scale measure? So I got a bathroom scale here. We're going to pause this. So what does a scale not measure? Doesn't measure mass. Doesn't measure weight, which is mg. What does a scale measure? Normal force. Normal force. Pause the video. What does a scale measure? Normal force. So, when I ask you to find what a scale reads, Nick, what am I really asking you to find? Which you're going to have to probably do a good free body diagram to figure out. This right here explains every amusement park ride you've ever gone on. A good amusement park ride does not change mg. We can't change gravity. We're not God. What it does is it changes how hard the chair that you're sitting on pushes up against you. What's another word for how hard the ground or the chair pushes up against you? All a good amusement park ride does is it mucks around with the normal force. Put your pencils down. Okay. This brings us to the famous Gracie elevator question. I like example one. You know what? Example one is going to be cloned. Actually, no, I have to do the whole thing because I don't think Edson and Jennifer have heard the rant. So, Edson and Jennifer, I normally say something like this. I like example one, I like example one, I like example one. Example one is a nice question. Josh, why would I say that? Did you hear me say it's going to be on the test? Or are you just the kind of student that notices when a teacher tends to emphasize certain things? Okay. I just told you it's going to be on there. Okay. Says this. A 72 kilogram man stands on a Newton scale in an elevator. The reason I made it a Newton scale is normally scales measure in kilograms. Let's just pretend ours measures in newtons. So we don't have to do a conversion. What does the scale read if the elevator is accelerating upwards at 3.2 meters per second squared? What does this question want me to find? Oh, boy. I thought someone was going to say what the scale reads, and I was prepared to say, what does this really want me to find? But Tato put two and two together, smarty pants, and he said, you know what? He's asking for a scale. No, he's not! What am I really asking for, Sarah? Normal force. This is a job for a free body diagram. Here's the free body diagram of this person. What are the forces acting on this person? Get the obvious one. Gravity. Is this person sinking into the ground like quicksand? Is this person flying into like Superman? So there is a normal force pushing up, bigger, smaller, or the same size as gravity. Which way is this person accelerating according to part A? Read the question. That's Newton's first. See how we're putting everything together now, Max? Newton's first tells me if he's accelerating up, normal force has to be bigger. What does this question want me to find? Scale normal force. Who's winning? Who's losing? What does winner minus loser always equal? What does this question want me to find? Oh, how would I get the Fn by itself? Oh, add the mg over? Cool, 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 cool. So I hear you. You're telling me normal force is going to be mg plus ma? Did they tell me the mass? 72. G, 9.8. Not negative. I took care of that negative in my winner minus loser. Plus 72 times 3.2. What do you get? Do that one in your head, Mr. Duke? Well, maybe. Oh, yeah, I can. It's going to be 72 times 13, so it's going to be 720 plus 360 is going to be 1,080 plus another 72 is going to be 1,152? Or am I totally off? I might be totally off. 72 times 13 is going to be 720 plus, I'm totally off. It's going to be 720 plus 206. It's going to be 926. Is that better? 36. Golly, 936. How many of you have been in an elevator before? When it's accelerating, first of all, when it's at rest, what's your acceleration? No, don't overcomplicate it. When it's at rest, what's your acceleration as a number exactly? That would be 0. When it's at rest, normal force is just mg. You feel normal. When it's going at a constant speed, what's your acceleration? 0. When it's going at a constant speed, you still feel your normal. When it's accelerating upwards, you feel gravity plus something. You feel heavier. B says accelerating upwards at 2.5 meters per second squared. I'm going to skip B. It's the same as part A. And I'm going to go straight to part C. Accelerating downwards at 5.2 meters per second squared. What does the question want me to find? The scale reading. What does it really want me to find? The normal force. Elliot, this is a job for a free body diagram. Elliot, what are the forces acting on this person? Get the obvious one.
Gravity.
Yep. Is this person sinking into the ground like quicksand? Are they flying into the air like Superman? Now, I'm not saying forces are balanced. Which way is this person accelerating? What's their acceleration downwards as a number? So are they in free fall? Because if they're in free fall, what would their acceleration be as a number? That means there must be a force up. But which way are they accelerating? So the normal force up, bigger, smaller, or the same size as mg? Do you see how we're able to use Newton's laws in a free body diagram to come up with a lot of information? Elliot, who's winning?
Mass of gravity.
By the way, it's not the mass of gravity, it's the force of gravity, or mg. And it's just easier to go mg. Be like me, abbrev. Okay. Who's the loser in this question? Yep. What does winner minus loser always equal? Yep. What are we trying to find? Scale reading. What are we trying to find? Normal force. Oh, what's right in front of the Fn? Ugh. No, not the mg. Right in front of the Fn. Ugh. I'm going to plus that to that side to get rid of the negative. At the same time, I'm going to minus the ma over. We've seen this dance before, yes? The two big ones you're going to do, by the way, either what you're finding is positive or it's negative. If it's negative, plus it over and move the other stuff to the other side. The mg drops down, minus ma, and if it's okay with you, Elliot, I'm going to put the normal force over here by itself. By the way, your normal is just mg, but when you're accelerating downwards, you're subtracting from mg. You feel lighter. That's what the little kid in the video experienced. And that's the one we don't get very often. Aside from elevators, which don't accelerate really big, there's not too many children's playground-y things that deliver a smaller normal force. There's plenty that deliver a bigger normal force, swing sets being a classic example. What's the mass?
72.
9.8 minus 72 times 5.2. What's the normal force? Crunch it, please. .2 units. It's a force. Newtons. And then I asked, as a little twist, what would that read in kilograms? So if you experienced a normal force of that and you stood on a kilogram scale, what would that read? How do I convert newtons to a kilogram mass? How do I go from a normal force back to kilograms? Divide by 9.8. So let's call this part B, 331.2 divide by 9.8. This person would feel like they had a mass of how much? Can I go 33.8? They would feel less than half their weight. By the way, an elevator would never accelerate like that. People would freak. Twilight Zone Tower of Terror, been on the Twilight Zone Tower of Terror? Okay. That one accelerates down, I think, at around 3 or 4 meters per second squared. So this would be even more intense than that. Elevator, I'll bet you, because the Twilight Zone Tower of Terror doesn't accelerate as fast as the elevator down. This is probably closer to what the elevator does on the way down. Okay. Is that okay? Skip D. E. Moving downwards at a constant velocity of 3.72 meters per second. Okay. What are the forces acting on this person? Get the obvious one. Gravity. What else? Normal force, which way? Up. Bigger, smaller, or the same size as gravity? Okay. Jason has made a terrific mistake. I'm glad he did, because the nice thing about my winner minus loser and free body diagram approach is as long as you keep your eyes open, you can make mistakes and catch them later. The mistake that you made is you didn't spot this phrase here, but that's okay. You targeted that word. That's okay. So based on downwards, who did you say is winning? No, based on downwards, who did you say was winning? You said gravity, yes? And so you would go winner minus loser equals MA. You would plus that over, you would minus that over, you would get gravity minus MA equals the normal force, and then you would say, okay, normal force equals 72 times 9.8 minus 72, and as long as, have I got on my rant about units being important? As long as you were clever enough to say, that's not an acceleration, hopefully you would, wait a minute, they didn't give me the acceleration. And then hopefully you would say, aha, what does constant velocity mean? By the way, this thought experiment here, this elevator experiment here, this is what led Einstein to general relativity, because here is when he realized, wait a minute, there is no way to detect acceleration if you're moving at a constant speed. But there's also no way to tell that you're at rest if you're moving at a constant speed. There is no experiment that can show whether you're moving or at rest. We can only detect acceleration. So you would go like that, and you would say, ha, hey, you know what? When the elevator is moving at a constant speed, you feel your normal. Pun sort of intended. You feel your normal mg. Your normal is just mg. That's the one all of you have grown up with. Every time you're standing, every time you're sitting, what you think of as gravity is actually the chair pushing up. And the reason I know that is when I jumped out of an airplane, have I mentioned that I jumped out of an airplane? When I jumped out of an airplane, I felt like I was weightless even though mg was acting on me. What was missing? Normal force. 72 times 9.8, well, 72 times 10 will be 720 minus 14.4, 705.6? Yeah. If you divide that by 9.8, you'll get exactly 72. On a scale, he would feel or she would feel their normal mass. Their normal. What if you're accelerating downwards at 9.8 meters per second squared in free fall? If you stood on a scale, what would the scale read? Prove it. You ready? What are the forces acting on this person? Get the obvious one. Gravity. I'm not sure, Mr. Dewick. Maybe the scale reads something. I'll put a tiny normal force in there just in case to hedge my bets. But I know I'm accelerating down, so who's winning? Gotta be. My equation has to be gravity minus normal force equals ma. And if I do my little dance of plussing the normal force that way and minusing ma that way, I get normal force equals mg minus ma. What's m? 72. What's g? 9.8 minus what's m? 72. According to this question, what's my acceleration? In your head, Matt, without a calculator, 72 times 9.8, take away 72 times 9.8 is what? Matt, 72 times 9.8, take away 72 times 9.8. What's anything take away itself? In other words, by the way, if you just tell me 0, I'll give you full marks, but here in our notes, we proved it. This is what I felt when I jumped out of an airplane. I mentioned that I jumped out of an airplane. This is what I felt. We're going to pause here. Your homework part 1. Here we go. Is section A. Just says circle the correct answers, and you can ask me about the answers later on in class. You can also try number 1. And you can try number 2. We're going to pause there. Let me pause the video.